In the previous clip, we saw that if we constrain to a straight line path, a plus tu, then we can understand the directional derivative of f in direction u at location a as being the derivative with respect to time of f of c of t evaluated when t is equal to 0. Notice that c of 0 is a, so that gives us the right location. Okay, so and so when we were looking at this before, we talked about this thing in terms of, we've got some limit as t goes to 0, f of the c of t minus f of c of 0 over t as t goes to 0, and it's a bit of a mess, right? So just like we saw for partial derivatives, and like you saw earlier in single variable calculus, there's a reasonably nasty limit quotient definition of a derivative, which is useful for proofs, but not at all for computing anything. And then there's some nice handy formulas for actually computing derivatives. And so that's what we're after right now. And the way that we're going to find that is by circling back and connecting it with the chain rule, because if you look at this expression, derivative of f of c of t, that of course is a composition of functions. So we're going to need to use chain rule. So the chain rule tells us that this is going to be the partial of f with respect to x times how fast x is changing with respect to time, plus the partial of f with respect to y times how fast y is changing with respect to time. And when you look at that, you see that it is actually the form of a dot product, as we've seen before. So this is df dx df dy dotted against x prime y prime. And so what are x prime and y prime? Well, we can find those by looking at our curve, because our location is given by this curve, because we constrained it to be moving along this path. It'll be helpful if I rewrite the curve in terms of coordinates. So the point A has x and y coordinate a1, a2, and our unit vector u has x coordinate u1 and y coordinate u2. So when I do the vector arithmetic to combine these two, I end up with something that has a first coordinate of a1 plus t u1 and a second coordinate of a2 plus t u2. And so then that tells me what my x coordinate is and what my y coordinate is. And so if I want to find out what x prime and y prime are, those are just the coordinates of c prime. So differentiating the first coordinate, a1 is a constant, so it's gone, and I differentiate tu1 with respect to t and I get u1, and differentiating the second one I get u2. So what we find is, in fact, that this is just the gradient of f dotted against u, which is fantastic. So now if we want to find out what the derivative of f at a in direction u is, all we have to do is evaluate this thing on the previous line when t is equal to a. So we just evaluate the gradient at a. The unit vector is a constant. And that gives us a short, quick, lovely formula that we should use for computations. You don't want to use that limit quotient form.